Earth is not the best planet for life. That statement sounds wrong, almost heretical. We are here, after all, thriving on this blue marble spinning through the void. But what if everything we assume about our world being optimal is just comfortable bias? What if there are planets out there, orbiting distant stars, where life doesn't just survive but flourishes in ways Earth could never support? These worlds exist. Scientists call them superhabitable planets. They are not science fiction or theoretical daydreams. They are real places identified through decades of planetary research, worlds where conditions for life surpass what Earth offers. Larger oceans, more stable climates, longer periods of biological development. This is about understanding what makes a planet truly ideal for life and confronting the unsettling possibility that we might be living on a backup option. Let's start with something most people never question: Earth's size. We think of our planet as just right, perfectly balanced. But from a biological perspective, Earth sits on the smaller end of what works. A planet with more mass, say 20 to 30% larger than Earth, creates advantages we lack entirely. More surface area means more ecological niches, more room for biodiversity to explode into forms we cannot imagine. Greater mass generates stronger gravity, which holds onto atmosphere more efficiently. That thicker atmosphere provides better protection from radiation, retains heat more evenly, and creates more stable weather patterns. Mars lost most of its atmosphere because it was too small. Its weak gravity could not hold on to those gases against the solar wind. Earth holds its atmosphere, but just barely in cosmic terms. A superhabitable planet with greater mass would clutch its atmosphere like a fortress, maintaining stable conditions for billions of years without the constant geological recycling Earth requires. Then there is the question of water. Earth is roughly 70% ocean, and we celebrate that fact as proof of our planet's hospitality. But consider this. Most of Earth's land masses are isolated or poorly distributed. Antarctica is locked under ice. Much of our land sits at extremes of temperature or elevation that limit biological complexity. A planet with more water, perhaps 80 or 90% ocean coverage, would have archipelagos instead of continents. Chains of islands scattered across the globe, each one a laboratory for evolution. Ocean currents would distribute heat more evenly. No massive continental interiors baking under relentless sun or freezing in perpetual winter. Just moderate, stable conditions everywhere. Island ecosystems on Earth, isolated and resource-limited, have produced some of the most unique species ever discovered. Now imagine an entire planet functioning that way. The Galapagos effect scaled up 1,000,000 times. Our Sun is another problem we rarely acknowledge. The Sun is a G-type yellow dwarf star, and it is frankly mediocre for supporting life long-term. It burns hot and fast. In another billion years, maybe less, the Sun will expand enough to make Earth uninhabitable. The oceans will boil away. The atmosphere will strip off into space. Everything dies. That is not some distant abstract future. In geological terms, it is right around the corner. K-type orange dwarf stars are different. Cooler than our Sun, yes, but far more stable. A K-dwarf burns its fuel slowly, living not for 10 billion years like the Sun, but for 20, 30, even 40 billion years. That is 2 to 4 times longer for life to evolve, adapt, and develop complexity. On Earth, it took nearly 4 billion years for intelligent life to emerge. Imagine what could happen with double or triple that time. The possibilities stop being about whether intelligence emerges and start being about how many times it emerges and what forms it takes. K-dwarfs also produce less ultraviolet radiation. UV light damages DNA. It mutates genetic material in ways that are usually harmful. Earth's ozone layer protects us, but only partially. A planet orbiting a K-dwarf would bathe in gentler light, reducing mutation rates and allowing life to evolve with fewer genetic errors. Stability, not chaos, becomes the baseline. Temperature matters more than most people realize. Earth's climate swings wildly over geological time. Ice ages erase ecosystems. Hothouse periods turn temperate zones into deserts. These swings are not gentle nudges. They are catastrophic resets that wipe out species and force evolution to start over. A superhabitable planet would minimize these swings. How? Through a combination of factors. A larger ocean acts as a thermal buffer, absorbing and releasing heat slowly. A thicker atmosphere distributes warmth more evenly from equator to poles. An orbit slightly more circular than Earth's prevents seasonal extremes. The result is a planet where temperature stays within a narrow band for hundreds of millions of years. Life thrives on stability. Evolutionary experiments need time to play out. On Earth, just as complex ecosystems develop, an ice age arrives and scrapes the slate clean. A superhabitable planet would give life the gift of time, uninterrupted time to build, diversify, and optimize. Then there is the matter of plate tectonics. Earth's shifting crustal plates recycle nutrients, regulate atmospheric carbon dioxide, and create diverse topography. This is good. But it is also violent. Earthquakes, volcanic eruptions, sudden mountain ranges thrusting upward and destroying habitats. Plate tectonics on Earth is a double-edged sword. A superhabitable planet might have a different setup. Perhaps a single-plate system with volcanic activity concentrated in specific zones, providing nutrient cycling without the constant destruction. Or maybe a slower, gentler form of tectonics that recycles material over much longer timescales. The key is balance. Enough geological activity to sustain a dynamic biosphere, but not so much that it constantly tears ecosystems apart. Magnetic fields protect planets from stellar radiation. Earth's magnetic field, generated by its molten iron core, deflects solar wind and cosmic rays. Without it, our atmosphere would erode like Mars. A superhabitable planet needs a strong, stable magnetic field, and a larger planet with a more massive core would generate exactly that. Stronger magnetism means better protection, which means a more stable atmosphere, which means life is not constantly being irradiated or having its environment stripped away. So far, we have established that a superhabitable planet would be larger, have more water, orbit a longer-lived star, and possess geological and magnetic stability beyond what Earth offers. But identifying these criteria is one thing. Finding actual planets that meet them is another. The first step involves looking at the right stars. K-type orange dwarfs are the sweet spot. Not too hot, not too dim, and they last long enough for complex life to develop multiple times over. Astronomers have cataloged thousands of K-dwarfs within a few hundred light-years of Earth. Many of these stars have planetary systems. The question is whether any of those planets fall into the superhabitable zone. The habitable zone, often called the Goldilocks zone, is the region around a star where liquid water can exist on a planet's surface. For a G-type star like the Sun, this zone is relatively narrow. For K-dwarfs, the habitable zone sits closer to the star because K-dwarfs emit less energy. But here is the critical part. The habitable zone is just the starting point. A planet can be in the habitable zone and still be a terrible place for life. Venus is technically in the Sun's habitable zone, and it is a hellish pressure cooker with surface temperatures hot enough to melt lead. What makes a planet superhabitable is not just location but a combination of size, composition, atmospheric thickness, water content, and geological activity. These factors must align precisely. A planet too close to its star gets tidally locked, with one side perpetually facing the star and the other in eternal darkness. A planet too far out freezes solid. The orbit must be nearly circular to avoid extreme seasonal temperature swings. The planet must have the right mass to hold onto its atmosphere but not so much mass that surface gravity crushes potential life forms. Finding planets that meet all these criteria is extraordinarily difficult. Until recently, we could only detect massive planets, gas giants like Jupiter, orbiting close to their stars. These so-called hot Jupiters told us nothing about smaller rocky worlds in habitable zones. Then our technology improved. The Kepler Space Telescope, launched in 2009, changed everything. Kepler stared at a single patch of sky for years, monitoring the brightness of over 150,000 stars. When a planet passes in front of its star from our perspective, the star's light dims slightly. By measuring these tiny dips in brightness, Kepler detected thousands of planets, many of them rocky worlds roughly Earth-sized or larger, orbiting within their star's habitable zone. Among those discoveries, certain planets started standing out. Not because they were Earth clones, but because they had characteristics suggesting they might be more habitable than Earth. Kepler 442b, for instance, orbits a K-dwarf star about 1,200 light-years away. It is roughly 30% larger than Earth, placing it in the ideal size range for a superhabitable planet. Its orbit lies well within the habitable zone, and its star is cooler and longer-lived than the Sun. Kepler 442b receives about 70% of the light Earth gets from the Sun, which might sound dim, but with a thicker atmosphere, the planet could retain enough heat to maintain liquid water across its surface. Another candidate is Kepler 62f, located about 1,200 light-years away in the constellation Lyra. This planet is about 40% larger than Earth and orbits a K-dwarf every 267 days. Its size suggests it could have a thick atmosphere and extensive oceans. Computer models indicate that with the right atmospheric composition, Kepler 62f could be entirely covered in water with scattered island chains, exactly the configuration that maximizes biological diversity and climate stability. These planets are not confirmed as superhabitable. We cannot visit them, cannot sample their atmospheres or study their surfaces directly. But based on what we know about planetary science, they fit the profile. They are larger than Earth, orbit longer-lived stars, and sit in stable habitable zones. They represent the first concrete examples of worlds that might not just support life but support it better than Earth ever could. The implications are staggering. If superhabitable planets are common, then Earth is not the template for life in the universe. It is just one example, and possibly not even a particularly good one. Life might be far more widespread than we imagine, thriving on worlds we have barely begun to understand. And if we ever develop the technology to reach these planets, humanity might find itself face to face with ecosystems that make Earth look barren by comparison. But before we get ahead of ourselves, we need to understand what life on these worlds might actually look like. Not science fiction fantasies, but biological realities based on environmental conditions we can predict. That is where the real story begins. Life on a superhabitable planet would not resemble the familiar patterns we see on Earth. The differences are not superficial. They are fundamental, driven by environmental conditions that push biological evolution in entirely new directions. To understand this, we need to think about what drives adaptation. Life does not evolve in a vacuum. It responds to pressure, to opportunity, to the specific constraints and advantages of its environment. Change the environment, and you change the rules of survival. Start with size. If a planet is larger than Earth, it has stronger gravity. Not crushing gravity like on a gas giant, but enough to make a measurable difference. On a world 30 to 50% larger than Earth, everything would be shorter, wider, more compact. Trees would not grow as tall because the energy cost of pumping water upward increases with gravity. Instead, forests might consist of dense, low canopy vegetation spreading horizontally rather than vertically. Animals would be stockier, built closer to the ground. Long limbs are a liability when every movement requires more force. Evolution favors efficiency, and on a high-gravity world, that means compact, muscular body plans. Flight becomes harder. Birds on Earth already operate at the edge of what is physically possible. Increase gravity by even 20%, and many flying species would be grounded. But that does not mean the skies would be empty. Evolution is relentless. If flight offers enough advantage, life finds a way. We might see creatures with broader wingspans, slower flight speeds, or entirely different methods of staying airborne. Gliding could become more common than powered flight. Or perhaps life skips the skies altogether and invests that energy into aquatic or subterranean adaptations. Water changes everything. A superhabitable planet with extensive oceans and island continents would create conditions unlike anything we see on Earth today. Water moderates temperature, distributes heat, and provides a stable medium for life. On Earth, the vast majority of biodiversity exists in tropical regions near the equator. Temperate and polar zones support far less life because temperature extremes limit what can survive. But on a planet with deeper oceans and more water coverage, temperature extremes would be minimal. Ocean currents would carry warmth from the equator toward the poles, creating a more uniform global climate. Instead of distinct biomes, ice caps, deserts, rainforests, you might have gradual transitions. A planet where every latitude supports abundant life. The evolutionary pressure that drives specialization on Earth, the need to survive harsh winters or scorching summers, would be absent. Life could diversify without facing existential seasonal threats. That does not mean everything becomes easy. Competition intensifies when resources are abundant. On Earth, harsh environments act as filters. Only the most adapted species survive in deserts or tundras. Remove those filters, and you get a different kind of challenge. Every niche is occupied. Every food source is contested. Evolution becomes an arms race not against the environment, but against other organisms. Predators become more sophisticated because prey has more options for escape. Plants develop more complex chemical defenses because herbivores have no seasonal die-offs to limit their populations. Ecosystems become dense, layered, and interdependent in ways that make Earth's rainforests look simple. Then there is the star. K-dwarf stars are smaller, cooler, and longer-lived than our Sun. A planet orbiting a K-dwarf receives less intense radiation, but that radiation is shifted toward the red end of the spectrum. Photosynthesis on Earth relies on chlorophyll, which absorbs blue and red light and reflects green. That is why plants are green. On a planet orbiting a K-dwarf, photosynthesis might evolve differently. If the dominant wavelengths are in the red and near-infrared range, plants might absorb those wavelengths and reflect others. Forests could be dark red, purple, even black. A black forest sounds alien, but it makes perfect sense. If you want to capture as much light as possible from a dimmer star, you reflect as little as possible. Evolution does not care about aesthetics. It optimizes for energy capture. The longer lifespan of K-dwarf stars introduces another factor. These stars burn steadily for tens of billions of years, far longer than our Sun's 10 billion-year lifespan. That means life has more time to evolve. On Earth, complex life took billions of years to emerge. Multicellular organisms appeared roughly 600 million years ago. Dinosaurs dominated for 165 million years before an asteroid reset the clock. Mammals took tens of millions of years to diversify after that. Humans appeared only in the last few 100,000 years. Now imagine a planet where the star remains stable not for 10 billion years, but for 30 or 40 billion years. Evolution does not stop. It continues refining, experimenting, diversifying. Life on such a world might be incomprehensibly advanced compared to anything on Earth. Not advanced in the sense of technology, but in biological complexity. Ecosystems so finely tuned that every species fits into a web of interdependence we could barely map. Organisms with sensory systems we cannot imagine, communication methods we would not recognize, survival strategies that exploit environmental niches Earth does not even have. Consider intelligence. On Earth, intelligence evolved relatively recently and only in a few lineages. Primates, cetaceans, corvids, cephalopods. Intelligence is expensive. Brains consume enormous amounts of energy. On Earth, the evolutionary pressure to develop intelligence is balanced against the metabolic cost. But on a superhabitable planet with abundant resources and stable climates, that cost-benefit calculation changes. If food is plentiful and survival does not require constant physical adaptation to harsh conditions, intelligence becomes a more viable strategy. Social cooperation, problem-solving, long-term planning, these traits could evolve more frequently and in more diverse forms. You might have multiple intelligent species coexisting, each occupying different ecological roles. Or intelligence could emerge in forms we would not recognize. Distributed cognition in colonial organisms. Chemical communication networks in plant-like species. Intelligence is not one thing. It is a spectrum of problem-solving strategies, and a superhabitable planet might host variations Earth never produced. Atmospheric composition also matters. Earth's atmosphere is roughly 78% nitrogen and 21% oxygen. That oxygen level is high enough to support complex life but low enough that wildfires do not spiral out of control. A superhabitable planet might have a slightly different balance. More oxygen increases metabolic efficiency. Insects on Earth grew to massive sizes during the Carboniferous period when oxygen levels spiked to 35%. Dragonflies with wingspans over 2 feet. Millipedes the size of cars. More oxygen means more energy available for cellular respiration, which allows for larger, more active organisms. But too much oxygen creates problems. Fires become uncontrollable. Oxidative stress damages cells. Evolution would need to find a balance, and that balance might be different from Earth's. Perhaps a thicker atmosphere with more nitrogen and water vapor to buffer oxygen levels. Or perhaps life evolves better antioxidant systems to handle higher oxygen concentrations. Gravity, water, light, time, atmosphere. These factors do not exist in isolation. They interact, creating feedback loops that shape every aspect of biology. A planet with higher gravity and deeper oceans might see the evolution of marine organisms far larger than anything on Earth. Water supports weight more efficiently than air, and higher gravity is less of a constraint underwater. You could have oceanic ecosystems dominated by creatures the size of whales, or larger, occupying roles we cannot even conceptualize. Imagine apex predators that hunt in coordinated packs across thousands of miles of open ocean. Symbiotic relationships between species so complex that individuals cannot survive without their partners. Entire floating ecosystems, organic structures built by colonial organisms that drift across planetary currents, serving as habitats for thousands of other species. On land, the interplay between climate stability and biodiversity creates a different dynamic. Earth's climate has been relatively unstable over geological time. Ice ages, warm periods, shifting continents. Each change forces mass extinctions and evolutionary resets. A superhabitable planet with a stable climate does not face those resets. Life builds continuously, layering complexity over millions of years without catastrophic interruptions. The result is ecosystems where every species is a specialist, where niches are subdivided into finer and finer categories. On Earth, generalists often survive extinction events because they can adapt to changing conditions. On a superhabitable planet, specialists thrive because conditions never change enough to wipe them out. But stability has a cost. Evolution is driven by pressure. Remove the pressure, and innovation slows. Earth's violent history, asteroid impacts, volcanic eruptions, climate swings, has been a crucible. Life adapts or dies. That constant threat drives rapid evolution, forces organisms to develop new strategies, new structures, new behaviors. A superhabitable planet might lack that urgency. Life becomes refined rather than revolutionary. Ecosystems reach equilibrium and stay there for millions of years. That does not make them less complex, but it changes the trajectory. Instead of dramatic leaps, you get incremental optimization. Instead of sudden bursts of diversity, you get slow, steady elaboration. None of this is speculation. It is extrapolation based on principles we understand. Gravity affects body structure. Water moderates climate. Stellar lifespan determines evolutionary timescales. We cannot observe these planets up close, not yet. But we can model them. We can predict how life would respond to these conditions. And the picture that emerges is one of worlds where life is not just possible, but thriving in ways Earth never allowed. The question is not whether these planets exist. We have already found candidates. The question is what we do with that knowledge. And whether we are prepared for what we might find when we finally develop the tools to study these worlds in detail. Those tools are closer than most people realize. Within the next decade, the James Webb Space Telescope and next-generation observatories will begin analyzing the atmospheres of potentially habitable planets. We are not just searching for oxygen or water vapor anymore. We are looking for biosignatures, chemical combinations that cannot exist without biological processes. Phosphine in the atmosphere of Venus caused debates for this exact reason. On Earth, phosphine is almost exclusively produced by life or industrial activity. Finding it on Venus, where temperatures and pressures are extreme, raises questions. Is it contamination? Geological processes we do not understand? Or something else entirely? Superhabitable planets offer clearer targets. If we detect oxygen alongside methane on a planet orbiting a K-type star, that is significant. Both gases react with each other. Their coexistence suggests active replenishment, something producing them faster than they destroy each other. On Earth, that something is life. Photosynthetic organisms produce oxygen. Methanogenic bacteria produce methane. Together, they create a chemical signature visible from light years away. But biosignatures are not guarantees. They are probabilities. A planet might have oxygen from photodissociation, where ultraviolet light splits water molecules. Methane might come from volcanic activity or subsurface chemistry. Confirming life requires ruling out every non-biological explanation. That takes time, multiple observations, and instruments we are still building. The challenge is not just technical. It is conceptual. We are looking for life using Earth as a reference. What if life on a superhabitable planet does not resemble anything we know? What if it uses different biochemistry, different energy sources, different structural principles? Silicon-based life has been a staple of science fiction for decades. On Earth, carbon dominates because it forms stable bonds with many elements, creating the complex molecules necessary for life. Silicon can do something similar, but its chemistry is less versatile. Silicon-oxygen bonds are too strong, making it harder to build dynamic, flexible structures. On a planet with different temperatures, pressures, or chemical availability, silicon might work differently. High-pressure environments could stabilize silicon compounds that break apart on Earth. A colder planet might slow chemical reactions enough to make silicon-based metabolism viable. We cannot rule it out. But carbon remains the safer bet. It works across a wider range of conditions. Life is opportunistic. It uses what is available. On superhabitable planets, where conditions are stable and resources abundant, carbon-based life would have every advantage. The diversity would not come from exotic chemistry but from the endless variations possible within carbon-based frameworks. Consider the variety on Earth. Single-celled bacteria, multicellular plants, fungi, animals with nervous systems complex enough to produce consciousness. All of that from the same basic biochemistry. Now extend that diversity across a planet with twice the biodiversity, 10 times the evolutionary time, and environmental stability Earth never achieved. You do not need alien biochemistry to get alien life. You just need more time and better conditions. The question of intelligence follows naturally. If life thrives on superhabitable planets, does that increase the chances of intelligent life? The Drake equation suggests yes. More habitable planets mean more opportunities for life to emerge. More time for evolution means more chances for complexity. But intelligence is not inevitable. On Earth, it took over 3 billion years to go from single-celled organisms to multicellular life. Another 500 million to reach anything resembling complex cognition. Intelligence is expensive. Brains consume enormous energy. A human brain is roughly 2% of body mass but uses 20% of total energy. That is sustainable only in environments where food is reliable and predictable. Superhabitable planets, with their stable climates and abundant resources, might favor intelligence. Or they might not. Stability can remove the pressure that drives innovation. On Earth, climate shifts force species to adapt or die. Tool use, social cooperation, abstract thinking, these traits emerged in environments where survival was difficult. Remove that difficulty, and evolution might optimize for efficiency rather than innovation. A stable ecosystem does not reward risk-taking. It rewards organisms that fit perfectly into existing niches. Intelligence, with its high energy cost and slow development, might be outcompeted by simpler, more efficient strategies. Alternatively, stability might enable intelligence in ways Earth's volatility prevented. Long-lived species with extended parental care could accumulate knowledge across generations. social structures could become more complex without the constant disruption of environmental collapse. Cultural evolution, the transmission of learned behaviors, might accelerate beyond anything seen on Earth. We do not know. The sample size is 1. Earth is the only planet where we can study the relationship between environment and intelligence. Superhabitable planets will provide more data, but only if we find them and only if we develop methods to detect intelligence from interstellar distances. Radio signals are one approach. The search for extraterrestrial intelligence has been scanning for artificial transmissions for decades. So far, nothing. But SETI focuses primarily on Sun-like stars. Expanding to K-type stars, where superhabitable planets are more likely, broadens the search. K-type stars live longer, giving intelligent life more time to develop and more time to broadcast signals. If a civilization around a K-type star began transmitting 1 billion years ago, those signals are still traveling through space. We just need to be listening in the right direction. Technosignatures go beyond radio. Industrial pollutants in an atmosphere, artificial lights on a planet's night side, megastructures built around stars for energy collection. These are all detectable, in theory, with sufficiently advanced instruments. The Kepler Space Telescope detected thousands of exoplanets by measuring the dimming of starlight as planets pass in front of their stars. Future telescopes could detect patterns in that dimming, irregularities suggesting artificial structures. A Dyson swarm, for example, a network of solar collectors orbiting a star, would create a distinctive light signature. Not solid, not natural, but fragmented and periodic. We are not there yet. Current technology cannot resolve those details. But the trajectory is clear. Every generation of telescopes improves resolution, sensitivity, and analytical capability. The instruments being designed now will be obsolete before they launch, replaced by concepts we have not imagined yet. That is the nature of progress. And it is why the discovery of superhabitable planets matters now. They give us targets. Specific places to point our instruments when the technology catches up. Without targets, we are searching blind. With them, we focus resources on the most promising candidates. Prioritization becomes possible. Not every exoplanet deserves equal attention. Rocky planets in the habitable zone of K-type stars, with evidence of water and stable atmospheres, move to the top of the list. Gas giants, planets too close or too far from their stars, worlds with extreme axial tilts or eccentric orbits, these drop lower. That does not mean they are uninteresting. But if the goal is finding life, especially complex life, superhabitable planets are the logical starting point. The implications extend beyond biology. Understanding superhabitable planets reshapes our perspective on planetary science, climate modeling, and even philosophy. If Earth is not the ideal template for life, then our models of habitability need revision. We have spent decades refining criteria based on Earth-like conditions. Temperature ranges, atmospheric composition, magnetic fields, plate tectonics. All of these are important. But they are not prescriptive. They describe one path to habitability, not the only path. Superhabitable planets suggest alternatives. Maybe plate tectonics is not necessary if a planet has other mechanisms for recycling nutrients. Maybe a strong magnetic field is less critical if the atmosphere is thick enough to block radiation. Maybe axial tilt variation, which drives Earth's seasons, is less important than overall climate stability. Each assumption we challenge opens new possibilities. And each possibility expands the number of planets we consider habitable. That has consequences. If habitability is more common than we thought, then life might be more common. And if life is more common, then the absence of detectable intelligence becomes more puzzling. The Fermi Paradox asks why, in a universe billions of years old with billions of galaxies, we have not encountered evidence of other civilizations. Superhabitable planets make that question sharper. If conditions for life are better elsewhere, if evolution has had more time, if ecosystems are more stable, then where is everyone? One answer is that intelligence is rare, even on ideal planets. Another is that intelligent civilizations do not last. They destroy themselves through war, resource depletion, or environmental collapse before they achieve interstellar communication. A third possibility is that we are looking in the wrong places or listening for the wrong signals. Intelligence might not broadcast. It might not build megastructures. It might prioritize sustainability over expansion, blending seamlessly into its environment rather than dominating it. None of these answers are satisfying. They all rely on speculation. But they frame the search. If superhabitable planets are common and life is common, then the filters preventing intelligence or technological civilization must be significant. Identifying those filters becomes as important as finding life itself. Understanding those filters requires looking at Earth's history differently. Not as a success story, but as a sequence of near failures. Life survived here despite catastrophic events, not because conditions were perfect. That reframes everything. If Earth barely made it through multiple extinction events, then maybe survival is the exception, not the rule. The fossil record shows 5 major mass extinctions over the past 500 million years. Each one wiped out more than half of existing species. The Permian extinction eliminated 90% of marine life and 70% of terrestrial vertebrates. Recovery took millions of years. And those are just the events large enough to leave clear geological signatures. Smaller disruptions happened constantly. Climate shifts, volcanic eruptions, asteroid impacts, changes in ocean chemistry. Any one of them could have pushed Earth past the point of recovery. But they didn't. Why not? Partially luck. Partially resilience built into ecosystems through diversity. When one lineage collapsed, another adapted to fill the gap. Life persisted not because Earth was ideal, but because life is flexible. That flexibility emerged from competition, predation, and environmental stress. Harsh conditions drove evolutionary innovation. Stable conditions might produce fewer innovations. If a superhabitable planet maintains steady climate for billions of years, does life evolve the same diversity? Or does it settle into equilibrium, optimized for current conditions but vulnerable to sudden change? We don't know. Earth's volatility might be a feature, not a bug. It forced life to develop backup systems, redundancy, and adaptability. Those traits became critical during extinction events. A planet with fewer disruptions might produce life that thrives under normal conditions but lacks the tools to survive catastrophe. That matters when considering long-term habitability. A planet might be superhabitable for 1 billion years, then face a single event that wipes out everything because the biosphere never developed resilience. Earth's biosphere survived because it was tested repeatedly. Each test eliminated the fragile and preserved the robust. Over time, that selection process built ecosystems capable of withstanding extreme stress. Superhabitable planets might skip that process. If conditions remain stable, evolution might not prioritize adaptability. Species would optimize for efficiency instead, becoming specialized rather than generalized. Specialization works until the environment changes. then it becomes a liability. Earth's generalists, the organisms capable of surviving in multiple environments, eating varied diets, and tolerating temperature fluctuations, those are the ones that made it through extinction events. Specialists vanished. That pattern repeats across the fossil record. So when we imagine life on superhabitable planets, we should consider whether stability breeds vulnerability. A planet with perfect conditions might host abundant life but lack the evolutionary pressure that builds resilience. One major disruption could end it all. Earth avoided that fate through repeated disruptions. Each one was a test. Most species failed, but enough survived to rebuild. That iterative process created a biosphere capable of enduring almost anything. Superhabitable planets might not have that advantage. And if they don't, their long-term prospects for complex life could be worse, not better. This introduces a paradox. The conditions most favorable for life in the short term might be unfavorable in the long term. Stability promotes growth but discourages adaptability. Instability limits growth but forces innovation. The ideal planet might be one that balances both. Stable enough to allow ecosystems to develop, but variable enough to maintain evolutionary pressure. Earth might actually occupy that middle ground. Not too stable, not too chaotic. Just volatile enough to keep life on its toes without wiping it out completely. If that's correct, then superhabitable planets are not necessarily better for the development of intelligence. Intelligence requires certain conditions. Large brains are metabolically expensive. They only evolve when the benefits outweigh the costs. On Earth, intelligence emerged in response to complex social dynamics, unpredictable environments, and competition for resources. Primates developed larger brains to navigate social hierarchies, remember food locations, and solve problems. Dolphins and whales did the same in ocean environments. Cephalopods evolved intelligence independently, using it to hunt, hide, and manipulate objects. Each case involved environmental challenges that rewarded cognitive flexibility. A planet with fewer challenges might not select for intelligence. If food is abundant, predators are few, and the environment is predictable, there's no evolutionary pressure to develop expensive brains. Life would thrive, but it might remain simple. That doesn't mean superhabitable planets are poor candidates for intelligence. It means we need to refine what we're looking for. A planet can be superhabitable for life in general while being less optimal for intelligence specifically. Those are different criteria. Intelligence requires instability, competition, and complexity. A planet that provides those conditions while maintaining overall habitability might be rarer than we thought. Earth might be unusual not because it's perfectly habitable, but because it's unstable enough to drive intelligence while remaining habitable enough to sustain it. That narrow range might be the real Goldilocks zone. Not temperature or water availability, but the balance between stability and chaos. Too much chaos and life never gets started. Too much stability and it never innovates. Earth sits somewhere in between. And if that balance is rare, then intelligent life might be rare even on planets where simple life is common. This brings us back to detection. When we search for biosignatures on exoplanets, we're looking for chemical evidence of life. Oxygen, methane, phosphine, compounds that don't persist in atmospheres without biological processes to replenish them. Those signals tell us life exists. They don't tell us whether it's complex or simple, intelligent or microbial. For that, we need technosignatures. Evidence of technology. Radio signals, industrial pollutants, artificial structures. things that only arise from civilizations capable of manipulating their environment on large scales. We've been searching for technosignatures since the 1960s. The results have been negative. Not a single confirmed detection. That absence is information. It suggests one of several possibilities. Either intelligent civilizations are extremely rare, or they don't last long, or they exist but don't broadcast signals we can detect. Each option has implications. If intelligence is rare, then Earth might be an outlier. Our combination of habitability, instability, and evolutionary pressure might occur infrequently. If civilizations don't last, then the window for detection is narrow. A species might develop technology, use it for a few thousand years, then collapse. In a galaxy billions of years old, we could be surrounded by ruins we'll never find. If civilizations exist but remain silent, then our search methods are flawed. We're listening for radio waves, but advanced societies might use communication methods we haven't imagined. Or they might prioritize stealth, avoiding detection to prevent attracting attention from hostile neighbors. None of these scenarios are comforting. They all suggest that contact, if it happens, will be difficult. But they also highlight the importance of continuing the search. Every null result refines our understanding. It tells us where not to look, what signals to ignore, which assumptions to revisit. And eventually, through elimination, we'll narrow the possibilities. Superhabitable planets add another layer to this process. If they're common and life is common, but intelligence remains undetected, then the filters are strong. Something prevents most life from reaching technological capability. Identifying that something becomes critical. Is it environmental? Biological? Sociological? The answer determines how we interpret the search and what we expect to find. Some researchers argue the filter is behind us. Earth passed through multiple bottlenecks early in its history. The origin of life, the development of eukaryotic cells, the emergence of multicellularity, each step was improbable. We made it through, but most planets don't. If that's true, then we're alone not because planets are rare, but because the path from chemistry to intelligence has too many obstacles. Others argue the filter is ahead. Life might be common, even complex life, but intelligence self-destructs. Climate change, nuclear war, artificial intelligence gone wrong. Technological civilizations create the tools for their own destruction. If that's the pattern, then the galaxy could be filled with planets where life flourished and then vanished, leaving no trace. Both scenarios are plausible. Both fit the evidence. Neither is testable without more data. That's why the search continues. Every exoplanet we study, every spectrum we analyze, every radio signal we monitor, adds information. Slowly, the picture clarifies. We're not looking for a single answer. We're mapping the distribution of possibilities. Where life is likely, where it's not, what conditions favor complexity, what prevents it. Superhabitable planets are part of that map. They represent one category of worlds, distinct from Earth analogs, with their own characteristics and implications. Studying them doesn't replace studying Earth-like planets. It complements it. The more categories we define, the better we understand the landscape of habitability. And the better we understand that landscape, the more effectively we can search. The search narrows when we recognize patterns. Superhabitable planets offer one pattern. K-type stars, orange dwarfs, provide another. They're cooler than the sun, longer-lived, and potentially more stable. Their habitable zones sit closer in, where tidal forces might lock planets, but orbital configurations can prevent that outcome. A planet in the right position around a K-dwarf could enjoy billions of years of stable conditions, far longer than Earth has experienced. That extended timeline matters. Evolution doesn't rush. Complex organisms require time to develop, diversify, and adapt. On Earth, multicellular life took roughly 3 billion years to emerge after the first cells appeared. Intelligence took another 500 million. If that pace is universal, then longevity becomes essential. A star that burns out quickly doesn't give evolution enough room to work. K-dwarfs burn slowly. Sun will last 100 billion years, far beyond the current age of the universe. Any planet orbiting one has time to spare. That advantage compounds when we consider stellar activity. Young stars flare violently, bombarding nearby planets with radiation. The Sun went through that phase early, but Earth's atmosphere and magnetic field provided protection. Not every planet gets that lucky. K-dwarfs flare less intensely. Their calmer nature reduces the risk of atmospheric stripping, making it easier for planets to retain water and develop stable climates. Combine longevity with stability, and K-dwarfs start looking like better hosts than Sun-like stars. But there's a complication. Smaller stars emit less light, so habitable zones are narrow and close. Planets in those zones receive tidal forces strong enough to lock one hemisphere toward the star. One side bakes in perpetual daylight, the other freezes in eternal night. That seems like a deal-breaker. How does life survive when half the planet is uninhabitable? The answer might lie in atmospheric circulation. A thick atmosphere can redistribute heat, transferring warmth from the day side to the night side. Models suggest that with enough atmospheric pressure, temperatures could stabilize across the surface. The day side wouldn't boil, the night side wouldn't freeze. Instead, a twilight zone between them could maintain temperate conditions indefinitely. That zone becomes the habitable region, a ring around the planet where life could thrive. It's not ideal, but it's viable. And viability is what matters. We're not searching for paradise. We're searching for places where chemistry can persist long enough to become biology. If a tidally locked planet with a thick atmosphere can maintain liquid water, it qualifies. Some researchers go further. They argue tidally locked planets might be more stable than rotating ones. Without day-night cycles, temperature swings diminish. Without seasons caused by axial tilt, climate becomes predictable. Life wouldn't need to adapt to changing conditions. It could specialize, optimizing for a narrow range of temperatures and light levels. That specialization could accelerate evolution in certain directions, producing complexity faster than on a variable world like Earth. It's speculative, but it fits the data. We don't yet know if tidally locked planets support life, but we can't rule it out. And if they do, then K-dwarfs suddenly become prime targets. They're common, making up about 12% of all stars. If their planets are habitable, then the number of potential biospheres multiplies. The galaxy becomes richer, more diverse, filled with environments we're only beginning to imagine. That diversity extends to other star types. M-dwarfs, red dwarfs, are even smaller and cooler than K-dwarfs. They make up 75% of all stars, and their planets are the easiest to detect. When a planet transits an M-dwarf, the star's light dims noticeably because the planet is large relative to the star. That makes characterization simpler. We can measure atmospheric composition, surface temperature, and orbital dynamics more accurately than around larger stars. But M-dwarfs come with problems. They flare frequently, especially when young. Those flares can strip atmospheres, sterilize surfaces, and prevent life from gaining a foothold. Their habitable zones are extremely close, increasing tidal locking and radiation exposure. And because they emit mostly infrared light, photosynthesis as we know it might not work. Plants on Earth use visible light. Under an M-dwarf, organisms would need to adapt to a redder spectrum. That's possible, but it adds another variable, another uncertainty. Still, ruling out M-dwarfs entirely would be premature. Some are quieter than others. Some planets might have strong magnetic fields or thick atmospheres that mitigate radiation. And photosynthesis isn't the only way to generate energy. Chemosynthesis works in darkness, using chemical reactions instead of light. If life can start with chemosynthesis and later adapt to dim red light, then M-dwarf planets remain in play. The point is this. Every star type offers trade-offs. G-type stars like the Sun are stable but short-lived. K-dwarfs last longer but lock their planets. M-dwarfs are common but violent. No category is perfect. Each presents challenges and opportunities. Our job isn't to find the perfect star. It's to understand which imperfections life can tolerate. And that brings us back to the core question. What does life actually require? We know the basics. Liquid water, energy sources, organic molecules, stable conditions. But how stable? How much energy? How complex do the molecules need to be? The answers determine where we focus our search. If life needs Earth-level stability, then we prioritize G-type stars with planets in wide orbits, minimal eccentricity, and protective gas giants nearby. If life tolerates more variation, then K-dwarfs and even M-dwarfs become viable. If life thrives under extreme conditions, then we expand the search to moons, rogue planets, and subsurface oceans. Each possibility requires different detection methods. Atmospheric biosignatures work for planets with atmospheres. Surface observations work for planets with transparent skies. Indirect signs, like unusual chemical imbalances or thermal anomalies, work for hidden biospheres. We're developing tools for all of them. The James Webb Space Telescope can analyze exoplanet atmospheres in unprecedented detail. Ground-based observatories are improving resolution and sensitivity. Future missions will directly image planets, separating their light from their stars and revealing surface features. These tools won't give us definitive answers immediately. Detection is hard, confirmation harder. But they'll provide data we didn't have before. They'll show us which planets have atmospheres, which atmospheres contain oxygen or methane, which surfaces reflect light in ways consistent with liquid water. From there, we infer. We build models. We test hypotheses. And gradually, the picture sharpens. Some researchers advocate for a broader approach. Instead of focusing on biosignatures, they suggest looking for technosignatures, signs of technology. Radio signals, laser pulses, megastructures that block starlight. If intelligent civilizations exist, they might be easier to detect than microbial life. A single radio transmission can cross light years. A bacterium can't. The challenge is distinguishing artificial signals from natural phenomena. Pulsars emit regular radio bursts. Quasars shine brightly across multiple wavelengths. Stellar flares mimic short pulses. Every time we detect something unusual, we have to eliminate natural explanations before considering artificial ones. That process takes time. In 1977, the WOW signal appeared in SETI data. A strong, narrowband signal lasting 72 seconds, originating from the direction of Sagittarius. It matched the profile of an artificial transmission, but it never repeated. Follow-up observations found nothing. Decades later, we still don't know what caused it. Was it alien? A satellite? A comet? The uncertainty remains. That's the nature of the search. We're looking for needles in a cosmic haystack, and most needles turn out to be straw. But we keep looking because the alternative, assuming we're alone without checking, is intellectually indefensible. If intelligent life exists, if civilizations are broadcasting, if technosignatures are out there, then finding them changes everything. Not just science, but philosophy, culture, our entire understanding of our place in the universe. Even negative results matter. If we search 1,000 star systems and find nothing, that tells us something. It sets constraints. It suggests intelligence is rare or short-lived or silent. Those constraints inform future searches and refine our models. They help us understand not just where life is, but why it's distributed the way it is. The search also drives innovation. Building better telescopes, developing new detection algorithms, refining atmospheric models, all of these advance our capabilities. Technologies created for exoplanet research find applications elsewhere. Medical imaging, climate modeling, communications. The search doesn't just answer questions. It generates tools that solve problems we didn't know we had. And it forces us to confront assumptions. Before exoplanets were discovered, many scientists assumed planetary systems resembled ours. Rocky planets near the star, gas giants farther out. Then we found hot Jupiters, gas giants orbiting closer than Mercury. We found super-Earths, planets larger than Earth but smaller than Neptune, a category that doesn't exist in our system. We found planets orbiting binary stars, planets with backward orbits, planets in wildly eccentric ellipses. The diversity exceeded predictions. It shattered assumptions. And it taught us that our solar system isn't the template. It's one example among countless variations. That lesson applies to life. We assume life needs water, but maybe some forms use ammonia or methane. We assume life needs moderate temperatures, but extremophiles on Earth thrive in boiling springs and frozen tundra. We assume life is carbon-based, but silicon shares similar bonding properties. Every assumption is testable. Every test expands our understanding. The search for life elsewhere is also a search for life's limits. How flexible is biology? How many forms can it take? How far can chemistry be pushed before it stops being life and becomes something else? These questions don't have easy answers, but exploring them matters. Not just for finding aliens, but for understanding ourselves. The search changes us. Every time we point a telescope at a distant star, every time we analyze an exoplanet's atmosphere, every time we consider the possibility of intelligence elsewhere, we're forced to see ourselves differently. We're no longer the inevitable result of cosmic processes. We're one outcome among many. That perspective shift matters. It reframes everything. Our conflicts, our ideologies, our territorial disputes, they all shrink when viewed against the backdrop of a universe potentially filled with other minds. It doesn't solve our problems, but it contextualizes them. It reminds us that whatever we're arguing about down here, We're all standing on the same fragile sphere, orbiting the same unremarkable star, in the same corner of the same galaxy. That's not sentimentality. That's perspective grounded in physics. And if we do find life, if we detect biosignatures in an exoplanet's atmosphere or receive a deliberate transmission from another civilization, the implications cascade outward in every direction. Science would gain new data. Philosophy would confront new questions. Theology would wrestle with new contexts. Culture would adapt. Politics would shift. Every institution built on assumptions about humanity's uniqueness would need to reconsider those foundations. But those changes wouldn't happen instantly. Discovery doesn't work that way. When exoplanets were first confirmed, the world didn't transform overnight. Scientists published papers. Engineers designed better instruments. Researchers refined their models. The process was gradual, methodical, built on incremental progress. Finding life would follow a similar trajectory. Initial detection, verification, analysis, interpretation. Each step would take time. Each step would generate new questions. And throughout that process, life on Earth would continue. People would still go to work. Children would still go to school. The sun would still rise. Discovery doesn't erase the ordinary. It adds layers to it. It gives context. It changes what we think about when we look up at night. But it doesn't stop the clock. It doesn't pause history. It becomes part of history, woven into the ongoing story of what we know and how we know it. That's why the search matters even before we find anything. The act of searching, the commitment to looking, the refusal to assume we're alone without checking, that itself is significant. It represents a choice. A decision to prioritize curiosity over comfort, knowledge over assumption. It reflects a belief that understanding the universe is worth the effort, even when the effort is enormous and the results are uncertain. And the effort is enormous. Searching for life requires coordination across disciplines. Astronomers identify candidate stars. Astrophysicists model planetary atmospheres. Chemists predict biosignature molecules. Biologists define what counts as life. Engineers build the instruments. Data scientists develop the algorithms. Every field contributes. Every contribution matters. The search is fundamentally collaborative, drawing on expertise from multiple domains, combining perspectives that wouldn't normally intersect. That collaboration produces unexpected insights. An astronomer studying stellar flares might notice a pattern useful to a climatologist. A chemist modeling atmospheric reactions might inspire a biologist rethinking metabolic pathways. Cross-pollination between fields accelerates progress in ways that isolated research can't match. The search creates connections, intellectual and institutional, that strengthen science as a whole. It also creates challenges. Funding is limited. Telescope time is competitive. Resources are finite. Researchers must justify their work, demonstrate progress, compete for support. That pressure can be frustrating, but it's also necessary. It forces rigor. It demands clarity. It ensures that the search remains grounded in testable hypotheses rather than drifting into speculation. And the search is iterative. Early missions provide data that inform later missions. Initial surveys identify promising targets. Follow-up observations refine our understanding. Each generation of instruments improves on the last. The James Webb Space Telescope detects molecules that Hubble couldn't. Future telescopes will detect molecules that Webb can't. The technology evolves. The questions sharpen. The search becomes more focused, more sophisticated, more capable of distinguishing signal from noise. That progression is essential because the universe doesn't make it easy. Distances are vast. Signals are faint. Noise is everywhere. Cosmic rays interfere with detectors. Stellar activity complicates atmospheric readings. Interstellar dust obscures light. Every observation fights against a universe that doesn't care whether we succeed. The universe isn't hostile, but it's indifferent. It doesn't hand us answers. We have to extract them, carefully, methodically, one data point at a time. And sometimes the data is ambiguous. A spectral line might indicate oxygen or it might indicate a false positive. A radio signal might be artificial or it might be interference. A temperature reading might suggest habitability or it might reflect instrument error. Ambiguity is constant. Certainty is rare. Scientists live in that tension, balancing evidence against doubt, confidence against humility. That balance is what separates science from belief. Belief doesn't require evidence. Science does. Belief can exist despite contradictions. Science must resolve them. The search for life operates entirely within the scientific framework. It asks questions that evidence can answer. It tests hypotheses that observations can confirm or refute. It builds models that data can support or undermine. Every claim is provisional. Every conclusion is subject to revision. That's not weakness. That's strength. It's what allows knowledge to grow. And knowledge is growing. Every year, we discover more exoplanets. Every year, we refine atmospheric models. Every year, we develop better instruments. The pace accelerates. The catalog expands. The possibilities multiply. Some planets are ruled out. Too hot, too cold, too irradiated, too unstable. Others move up the priority list. Temperate, rocky, orbiting stable stars, showing promising atmospheric signatures. The search narrows and broadens simultaneously. We eliminate candidates while identifying new ones. The process is dynamic, constantly adjusting based on incoming information. And the information keeps coming. Ground-based telescopes scan the sky. Space telescopes peer deeper into the cosmos. Radio arrays listen for signals. Every instrument contributes. Every dataset adds detail. The picture of the exoplanet population becomes clearer. We're learning not just where planets are, but what they're like. We're mapping compositions, measuring temperatures, detecting clouds, tracking weather patterns. We're transforming distant points of light into worlds with properties, characteristics, atmospheres. We're making them real in a way they weren't before. That transformation is gradual but profound. Decades ago, exoplanets were theoretical. Now they're cataloged. We know their masses, their orbits, their host stars. We estimate their surface conditions. We predict their climates. We assess their habitability. They've gone from speculation to data. And with each new discovery, with each refined measurement, the question becomes sharper. Not whether life exists elsewhere. The universe is too vast for Earth to be unique. But where? How common? How detectable? Those are the questions driving current research. Those are the questions that instruments are designed to answer. And the answers are coming. Maybe not tomorrow. Maybe not this decade. But they're coming. Every technological advance brings us closer. Every mission gathers more data. Every analysis refines our models. The trajectory is clear. We're moving toward a moment when we'll know. When ambiguity will resolve into certainty. When the question of life beyond Earth will shift from whether to where and what kind. That moment might arrive through atmospheric detection. A spectrum showing oxygen, methane, and phosphine together. Molecules that don't coexist without biological processes maintaining them. Or it might arrive through radio signals. A repeating pattern, narrowband, modulated, unmistakably artificial. Or it might arrive through direct imaging. A telescope resolving surface features on an exoplanet, detecting seasonal changes, observing patterns that suggest biology. However it arrives, the moment will be definitive. Not ambiguous. Not provisional. Clear. And when it comes, when we finally know with certainty that life exists beyond Earth, the search won't end. It will transform. From searching for life to studying it. From asking whether to asking how. From detection to characterization. New questions will emerge. How does their biology work? How did it originate? How does it compare to ours? What can we learn from it? The discovery won't close the book. It will open a new chapter. One we can't fully anticipate because we don't yet know what we'll find. But we're preparing. Building the tools. Training the researchers. Developing the frameworks. When the moment comes, we'll be ready. Not perfectly ready. Science never is. But ready enough to begin the next phase. Ready to take what we learn and push further. Ready to turn discovery into understanding. That's the real goal. Not just finding life, but understanding it. Not just detecting biosignatures, but interpreting them. Not just confirming we're not alone, but learning what that means. The search for life is ultimately a search for context. A way to understand ourselves by understanding what else is possible. And every answer we find generates new questions, deeper questions, questions we couldn't have asked before. That's how knowledge works. It doesn't converge toward completion. It expands toward complexity. The more we learn, the more we realize we don't know. But we keep learning anyway. Because the alternative is stagnation. Because curiosity demands answers. Because the universe is out there, vast and indifferent and full of secrets, and we've decided those secrets are worth pursuing. That decision defines us as much as any discovery will. Looking up changes nothing about the stars. They burn regardless of whether we notice. They die whether we watch or not. But looking up changes us. It repositions our place in a cosmos that wasn't designed around our existence. Every telescope pointed outward, every spectrum analyzed, every planet catalogued adds weight to a conclusion we're still processing. We are not special. Earth is not optimal. Life found a way here despite limitations, not because of advantages. Superhabitable planets force that recognition into sharper focus. They exist. K-type stars outlive our Sun by billions of years. Planets with deeper oceans distribute heat more efficiently. Larger worlds hold thicker atmospheres. The chemistry works. The physics supports it. These aren't fantasies. They're logical extensions of planetary science applied to environments we're only beginning to map. And if they're out there, if conditions exist that surpass what Earth offers, then every assumption about life's rarity needs recalibration. The implications don't stay confined to biology. They bleed into philosophy, culture, the frameworks we use to interpret meaning. If Earth is mediocre and we're here anyway, then the universe isn't hostile. It's indifferent. It doesn't care whether we thrive or collapse. That indifference is liberating once you accept it. It means survival isn't guaranteed, but it's possible. It means we're not owed anything, but we're not prohibited from anything either. The rules are physical, not moral. Gravity doesn't judge. Chemistry doesn't have preferences. We work within constraints, but those constraints are universal. Understanding superhabitable planets also reframes the Fermi Paradox. If better worlds exist and we haven't heard from anyone, the silence becomes heavier. Maybe intelligence is rare even on ideal planets. Maybe it emerges and self-destructs before it broadcasts. Maybe civilizations prioritize stealth over contact. Or maybe we're early. The universe is young in cosmological terms. Stars will burn for trillions of years. If intelligence takes billions of years to develop, we might be among the first. That's statistically unlikely but not impossible. Someone has to be first. The absence of signals doesn't prove we're alone. It proves detection is hard and the sample size is small. Every null result teaches us something. Every survey that finds no technosignatures narrows the parameters. Every atmospheric analysis that shows no biosignatures refines our models. Negative data isn't failure. It's information. It tells us where not to look, what assumptions to discard, which methods need improvement. Science advances through elimination as much as discovery. Ruling out possibilities is progress. But the search continues because the alternative is intellectual surrender. Assuming we're alone without checking is laziness disguised as humility. The universe is too large, too old, too chemically rich for Earth to be unique. Probability doesn't guarantee life elsewhere, but it makes the assumption of uniqueness untenable. So we build better instruments. We scan more stars. We analyze more atmospheres. We listen for signals. Not because we're certain we'll find something, but because the question matters enough to pursue. And when we do find life, whether it's microbial biosignatures in an exoplanet's atmosphere or a deliberate transmission from another civilization, the discovery won't answer everything. It will generate new questions. How did it start? How does it function? How does it compare to us? Each answer will spawn more inquiries, deeper investigations, frameworks we haven't developed yet. That's the trajectory of knowledge. It doesn't converge toward completion. It spirals outward, revealing complexity we didn't anticipate. The search for superhabitable planets is part of that spiral. It expands our definition of habitability beyond Earth's template. It challenges assumptions about what life requires and what conditions optimize biological complexity. It forces us to think in terms of distributions rather than absolutes. Not whether life exists, but where it's common, where it's rare, what factors determine its emergence and persistence. Those are the questions shaping current research. Those are the questions that instruments launching in the next decade are designed to address. We won't have all the answers soon. Detection takes time. Confirmation takes longer. But the tools are improving. The data is accumulating. The models are sharpening. We're closer now than we've ever been to knowing whether we're alone. And regardless of the answer, regardless of what we find or don't find, the act of searching matters. It represents a commitment to understanding over assumption, curiosity over comfort. It reflects a species willing to confront its own insignificance and keep asking questions anyway. That willingness is what separates us from the indifferent cosmos. The universe doesn't ask questions. We do. The universe doesn't search for meaning. We do. And in that search, in the refusal to accept ignorance as final, we define ourselves. Not as the center of creation, not as the pinnacle of evolution, but as observers capable of recognizing our own mediocrity and pushing past it anyway. Superhabitable planets exist. Life might thrive there in ways we can't imagine. And whether we ever reach them, whether we ever detect their inhabitants, whether we ever confirm their existence beyond theoretical models, the knowledge that they're possible changes how we see ourselves. We're not living on the best planet. We're living on the one we have. And that distinction, subtle as it is, reframes everything.